Hello, today I will be demonstrating W2 practice and demonstrate for 2300 lab. So in this practice we are tasked to create a full adder as a logic circuit that has 2 bits that are going to carry information on the output, sum and carry. But before we can do that, we must first create the XOR gate that's going to be used in this logic circuit using only NAND gates. So we're going to be creating this in CircuitVerse, but before we do that, we're going to be using Boolean algebra rules to demonstrate that Q is actually equivalent to A XOR B as provided here. So I went ahead and did the expressions in Microsoft Word, and we can see from the circuit above that this is what it's going to look like. We're going to have quite a few knots, and we can apply De Morgan's theorem to thus break this up into an OR and have a knot on each. Then we can use our double negation law to simplify this further. We're going to get this here, and once again we're going to apply De Morgan's theorem. Oops. We need De Morgan's theorem. And from here, we're going to use distribution of multiplication over addition, giving us this whole term here. But remember that A ANDed with A naught is just going to be 0. It's the complement law. And the same goes for B naught. So with 0 ORed, with these two terms, we have the annulment law, which thus leaves us, which gets rid of these zeros essentially, and leaves us with these terms. And when we think about it for a moment, like suppose A is 1 and B is 1, well, that would mean A naught is 0 here, B naught is 0 here. So 0 or 0, you get 0, but if only 1 is on, it's going to be true. So if A is 1 and B is 0, then we're going to get 1, 1. So 1 ANDed with 1 is just going to be 1. Or 0 ANDed with 0, I believe. And then we're going to essentially have output of 1. So we can see that these two are logically equivalent. Hence, Q is actually A XOR B. So we can build this. We can build this in CircuitVerse, but before we do that, we're going to demonstrate the full adder truth table. It's right here. I went through the liberty of making it in Excel. So essentially, this is going to add, or it's in a, well, yeah, full adder. Essentially, what's going to be happening is two values A and B are going to be added. So A added with B gives us 0, so 0 sum, 0 carry. And then, or I'm sorry, no, it appears all of them function, but nonetheless, this is our truth table. It's a long-winded process. All right. So we have our truth table. So we can build it in CircuitVerse. But in order to build it in CircuitVerse, we first have to create this XOR gate using a NAND gate. So once we have this XOR gate, we can then start making our full adder. And to do that, we got to full screen it. And as you can see right here, we can insert a sub-circuit and insert XOR as such. But we won't be needing it since we already have it built. So now all that's left is to demonstrate. So that all that's left is to demonstrate all the truth values on the table here. So we have all values is 0 here. As you can see, it's truthful to our truth table. And we're going to have C be 1. And we'll see that sum comes out to be 1 just like in the truth table. Next, we're just going to have B. It should have sum of 1, as we see here in the truth table. Then it's going to be B and C are 1. And we're going to see that carry has 1 here. The next part in the table, we're only going to have A as 1. And we have a sum of 1, as seen in the diagram and the truth table. Then C is going to be 1 as well. And we're going to have a carry of 1. Next part is to have 1, 1, 0. So A is 1, B is 1, C is 0. And we get a carry of 0 as provided in the truth table. And when all are 1, all inputs are 1, we should have a sum of 1 and a carry of 1, as we can see in the diagram. And before I end, I'll just kind of show my Excel equation here for each of the outputs. So that's the sum, and here's the carry. Thanks for watching.